Okay, so let's solve the week 11 topic number 2, which is something about the partial pressure problem. And then this also related to the understanding the limiting agent. And here's I just give you the generic equation that you probably easily see. We call the ICE problem, initial, change, and an equilibrium. Understanding that is how we going to figure this one out. A mixture of gases prepared from certain mass of gas, which is we can convert that into a number of moles, 12.7 of hydrogen. So after reaction of oxygen and hydrogen, so let's just write this one down first. Hydrogen, oxygen makes 2H2O. So that's a reaction that we are going to use. Okay. So let's use this, but before we need to figure it out what this meaning of 1887.5 grams of O2. So okay, so we know that the 32.0 grams of O2 per mole of O2, right? So that's a gram per mole. And so let me to make it easier, we'll just simplify this way. So therefore, what that means is number of moles of O2 is here in the beginning is 2.73 mole O2. I think I need more spaces here, so let's move in this one down to a little bit. Okay, and then the number 2, which is a 12.7 grams of hydrogen, and the molar mass of the hydrogen is 2.02 gram per mole for hydrogen. So that makes me hydrogen initial number of moles. That's a 6.29 mole of hydrogen. And so this is essentially initial condition. So I just wrote down this equation. When hydrogen and oxygen meets, they're going to react, and then I'm going to write ice. So initially you have 6.29 and then mole, and then the 2.73 moles of oxygen, and there's nothing. So for a change wise, we are going to one component is limiting agent. Okay, so this is called the limiting agent. And which is limiting agent? Think about it. If you use 2.73 moles, and that's 2 times 2.3, 2 times 2.73, that's 5 times 4, 6 mole, right? And then therefore you'll generate also 5 times 4, 6 moles of water. So you're going to lose, you're going to consume. Okay, so at the end, if you have an ice problem, and then this will be a 0.83 mole, which is for hydrogen. You have nothing left, and then you have a 5.46 moles of H2O. Right? Okay, so we kind of figured this one out, and then what is the total pressure of the mixture? The temperature is such and such, and the volume is given. Right? So they want to know the pressure of the gas. So finally, in the reaction mixture, in the beginning, you have those number of moles, but at the end, when you essentially reaction is complete, this is what is left in the reactor. Right? So the Therefore, ideal gas, the total number of moles, which is, let's just say N, which is, that is NH2 plus NH2O. So that will be a that can be something that can be added up, which is a 0.83, 5.46, 3, so 9, 2, and 6. Okay, so therefore the total number of moles is 6.29 moles. Okay, so that's what I can see. So now, what are the partial pressures? Okay, so the question now here is, what is a partial pressure of gases in the remaining mixtures? Okay, so the partial pressure pH2, PO2, pH2O. This one is simply obeying this the rule saying volume NH2 RT, and this one is 0 because there's nothing left at the end, and then this is a NH2O RT over volume. Okay, so now it's those are the partial pressures equation. The tricky part is now using this notation. Temperature is 162 degrees C and added by 273 Kelvin, and then make it 435 Kelvin. Okay, so you want to use the temperature in the unit of Kelvin, and then the volume is here. That's good. And then I guess the pressure will have a unit of the ATM, atmospheric pressure. That's my choice. So therefore, so this one is N, what was the N? Okay, 0.83, R 0.0821, T 45435, divided by volume 12.0. Okay, and so this one will be 2.5, and the unit is ATM. Once again, remember that R has a gas constant 0.0821 ATM a liter. Your pressure unit is ATM, and volume unit is a liter, and the mole and temperature unit must be in Kelvin. Okay, to be able to use this gas constant, you should follow the notations in the like that. Okay, the partial pressure of oxygen is nothing. There's none, and then this one is just nothing but doing the same math. 46, 0.0821, 435, 12.0 liter, and that will make it 16.2 ATM. Okay, and then so therefore, what's my total pressure? There are two ways. I mean, this is the same thing. The total pressure P is a combination of summation of all the partial pressures that is inside of this reactor. So O2 and pH2O, right? So therefore, it could be 2.5, 0, 16.2, and make it 18.7 ATM. So that's the total pressure. The other way is actually you can do the same thing, which is PV nRT. So nRT over V, and here's N is the one that's shown up here, which is a total number of moles of gases here. And so therefore 6.29, 0.0821, 435 divided by 12.0, that will give me 18.7 ATM. Okay, so it is a redundant way to solve the same problem. One universal relationship here is this, and then this is a partial pressure is an individual pressure contributions towards the total pressure will be known as measured as a P. So you can kind of visualize yourself. This is a wall, and this is a hydrogen gas makes a bounce, and then there is a H2O gas makes a bounce. Each gas make a bounce and contributes to the momentum changes that contributes to the pressure. So whether it's a collision of hydrogen or the water molecule to the wall, the pressure contribution is equally counted as one gas molecule collided on the wall. Okay, so that's why this simple equation, which is a summation of those, the partial pressure contribution has those kind of the concept here. Thank you for your attention.